Now we're going to talk about the next topic in quantum mechanics, which is how to calculate the so-called stationary states. Up till now, we've dealt with Schrödinger's equation, and we've looked at a solution for it in the case of a free particle that's unbound by anything and is free to travel in any direction. But we saw that bound particles in the Bohr model led to quantized variables. That meant either energy, or in the case of the atom in the Bohr model, the radii of orbits. We're going to see that this is a general property of all bound systems or all stationary states, like the analogous concept of the Bohr model, and this comes from something very simple. This comes from the idea of standing waves in classical physics, and the idea of wave-particle duality. So that if we have, for example, a classical string, there are certain wavelengths that fit on the string. And those are that lambda has to be 2L over n. L is the length of the string, and is an integer. So quantization happens in classical physics too. And as a result, this wave here is no longer a traveling wave, either moving to the left or the right. It's actually a standing wave. Or a superposition of a right traveling wave and a left traveling wave. As a result, the wave function in classical physics takes on a somewhat simplified form. It's some function of x times a sinusoid in time. And that's basically unchanged for any kind of system. The nodes aren't moving left and right. The whole system is just oscillating up and down. In quantum mechanics, stationary states, or states of definite energy, in other words, states that solve the Schrödinger equation, will have a definite form as well. If capital psi of x and t represents the matter wave for this particle in both position and time, it will decompose into a function little psi of x, e to the I omega t, e to the minus I omega t. And this creates the idea of or the analog of a standing wave. The term e to the minus I omega t will have important consequences for the energy and the momentum of the particle, but we'll talk about this later. If that's the form of the wave function, then notice this. the time derivative that appears in the Schrödinger equation has a rather simple form. Just get back my minus I omega in my original wave function. As a result, the Schrödinger equation has a somewhat simplified form. This is called the time-independent Schrödinger equation, and it's only true for energy states. Or stationary states. So it's a somewhat special case. It's not the general Schrödinger equation for any particle, but rather one for the special case of a stationary state. And it's somewhat simpler to use because it has one less derivative to worry about. Notice that what happened here is that the e to the minus I omega t has basically dropped out of all the terms. It was here, and it was here, and we've just divided by that factor. If we can't divide by the wave function psi, even though it just multiplies right here and here, because it's actually the derivative of psi, the second derivative that appears in that first term. As a result, what we have is a differential equation for this function psi of x that describes the particle, the standing wave for this bound state.